Hi, everybody. Hope you guys have been having a good workshop so far. My name is Archit Vasan, and I'll talk to you all about just like simply how to run Python and Jupyter Notebook on Polaris, and then Aditya will join in and talk about containers on Polaris and ALCF systems. So the general outline of this is that I'm first going to talk about, in general, how to use Python on like a terminal in Polaris. So things like managing Conda environments and then running single rank and multi-rank jobs. And then discussing how to use Jupyter Notebooks on Polaris. So the Jupyter Hub on Polaris, how to use that. And also working with machine learning modules on Jupyter Notebook. And finally, Aditya will discuss containers at ALCF. And so first off, an important point that you're probably all aware is if you want to use this machine, then you can log in as follows. And if you have any troubles, there's a lot of support that's available for you to use. And once you're in order to play around with using Python on this computer, you have to you can either request, like submit a job into the queue and then wait for it to run, or if you can also run interactively. And for the purpose of this workshop, please use these keywords. And so you'd want to request an interactive node. You'd want to request the project allocation fall W as 23 single, request one node or two nodes on the debug queue, and you can ask for a wall time of up to like an hour. And so finally, another point to note is that Polaris actually uses modules to control the loading of software environments. And so there are multiple pre-built environments that contain GPU-supported builds of Torch and TensorFlow and different Python modules. And an important point here is that I actually put in here module load 2023-01-10, but actually there's a newer module 2023-1004. So please be aware of that. So you just load in the module and you can do conda activate, and then this will then load in all of the multiple Python programs that you need to actually run your jobs. And if for any reason you need to use an older conda version because of any package that you need, you can load in an older version. So you can actually search for the available conda environments that are like available as modules, just doing module avail, which just means what are the available conda environments that can be loaded, and then just load the important environment. And then you just do conda activate, and then that'll let you use the Python programs in that environment. And so if you, for any reason, need more flexibility, so you need to install your own package, something that's not within the environment already, even though the environment has many Python programs that you might need, there might be something specific for your project that you might need to install. And so the way to get around this is to just create your own conda environment. And so you can just clone the base. So you can instantiate the module. And so once again, use the October 4th module here, not this one. And you can then just clone the base, which is the environment within that module, and then prefix is just going to install it into the place that you want to install it in. And then just activate the module, activate the environment. And a note here is, so your, an important note here actually is that if you want this environment to be properly functioning, then please install this within an interactive job. And so, yeah, another point to note is that once you have successfully either you're just using the default environments or you've installed your own module, you can now run your Python script simply by doing Python and then the example script. And once again, if you need any additional packages, then just activate the environment that you've created, and then you can either use Conda or pip to install your module. Okay, so now that we've discussed this, if you want to make use of the machine, like the multiple resources on the machine, then one way of doing this is to run a multi-rank job. So this is basically in order to parallelize your job across different ranks on the machine. And so this is done, you can run this across like 64 CPUs and 4 A100 GPUs on each of the compute nodes. So when you log into the interactive node, you're logging into a compute node. And then it's just a simple example of just running MPI exec, and then you ask for the number of processes that you want to run. And you can actually ask for multiple nodes on Polaris. And so you can just do proc per node, which is going to indicate the number of procedures per each node, and then you run. But in order to use MPI effectively with Python, there are multiple different packages you can use, like Ray. But something that's very useful is MPI for Pi, which will let you run a Python run on multiple nodes. And so the way that this works is, this is a very simple example. So this is like the hello world of MPI. So all you need to do is you just need to instantiate an MPI world, and then you can get important parameters such as the size or the rank that the specific run is on. And then all I'm doing here is I'm going into that, like the specific rank, and then it's just printing out the rank identifier. And so you can do more complicated things here with MPI for Pi as well. So you can also communicate between different ranks. So if you have something that's running on rank 0, you can communicate that to the other ranks as well by doing broadcasting and gathering. Okay, so now that I've discussed using Python on the machine itself, many of you are probably more comfortable with using Jupyter Notebooks. And those are available at ALCF as well. And so to access the Jupyter Hub, you can just access it right here at this website. And when you're there, just log into Polaris, as you can see here. And then once you're in the login, then it'll ask you to, first off, add your authentication. So you need to authenticate and log into the to the site itself. And then you can set up your servers, like your job options, as follows here. And so what you need to do is you need to indicate the appropriate queue name. And so what I'm choosing here is just debug if you're just running a relatively small job. And you would ask for the project list for this workshop. And then you can request either 1 to 2 nodes on the debug queue. And then you can ask for a runtime between 5 and 60 minutes. And then just ask for all, I usually just ask for all the file systems. And then just hit start. And then what this will do is this will put you in the queue. And then once the server's available, then you'll start the job. And then once you're there, the job will start, and then you can start a new notebook. And so there's just like a bunch of different types of jobs that you can start to start a new Jupyter Notebook. And so to use a Conda environment with several of the necessary Python modules, you just need to change the kernel to this thing. But actually, once again, you would want to change this to the newer version. So there's an October 4th version that you can change this to. So yeah, just change this. You would log in right in the red box at the very right corner, and then just load in October 4th here. And so here's a very simple example. This is just like, you can see that the default environment will give you access to a lot of different modules. What I'm just showing here is just NumPy and Matplotlib. and show that you can run a very simple Python script if you need to. So another note that you need to be aware of is that when you start this Jupyter Hub, it will start on your home folder. And so you might want access to things in your project spaces, so like your Grand or your Eagle spaces. And so if you want to access them, you can create a symbolic link to access these projects. So for example, here I'm just creating this link, so the ln-s, and then just linking it to my Grand space, and then creating a identifier, which is just, for me, just Grand Archit, my name. And you can then see that in the left-hand side, you'll see that there's a list of different types of, like different directories. And then you can access your Grand space, your Eagle space from Jupyter Hub. And so the final thing I would like to point out in regards to Jupyter Notebooks is that this module, so once again, the October 4th module here has access to several, like the machine learning modules that you'd be interested in. What I'm showing here is I'm showing TensorFlow and PyTorch. And so you can see that you can load in TensorFlow, and then you can see that there's like these available devices that are able to use. So TensorFlow is able to use the GPU on the machine. And you can also see that when you import Torch, then you can see that CUDA is also available to use on Polaris with Torch. And so that's all I have for these first two talks. And so I'll hand it over to Aditya now.
Thank you, Archit. Hi, I'm Aditya Tanikanti, and I'm here to present containers at ALCF. So in this talk, I'll try to first talk about what containers exactly are, and then I'll walk through a MPI example on Polaris. So think of containers as a software package which wraps both the software as well as all its dependencies within that package. And then once you have that package ready, you can it helps you to move it from one system architecture to the other quite easily with little to no changes. More often than not, they're compared to virtual machines. But the biggest difference between the virtual machine and a container, as you can see, is that virtual machine tends to have the guest operating system, and it also emulates the hardware, making it a little more resource intensive, whereas containers, they share the underlying kernel with other containers, and they're ephemeral as well, so they're much more lightweight than what a virtual machine is. And there's a link provided which goes through all the differences with the virtual machine. You can click on it and see what those differences are. I'm also talking about some of the advantages of using containers, where it's portable, lightweight, isolation, they're self-explanatory. If you're using a container orchestration tool like Kubernetes, it helps you scale up and down. Microservice is a good feature where, if your application tends to have several components and they need to talk to each other, each component can be a container of its own, and you can easily, it helps you, if there's any errors or issues, helps you debug much more easily. Version control, you can version the actual container image itself, as well as the definition or Docker file where you write instructions on how to build that container. You can version control them. CI/CD, and there's a strong ecosystem amongst other things. So these are some of the advantages. Now, at ALCF, we use Singularity. Singularity is the Docker runtime environment. Things to keep in mind is that, like, the several container runtimes, like the popular one is Docker. There's Podman, there's Containerd. But at ALCF, we support Singularity, and the reason for it is that it's built for supercomputers, and it's much more secure than the other container runtime technologies. Also, a thing to keep in mind is that Singularity has now joined the Linux Foundation. So they have renamed themselves to Aptena. So in the future machines, you'll probably see Aptena. Right now, I'll walk through a GitHub page, a GitHub code where I run an MPI example. But just to keep one thing to keep in mind is there are two ways to do this. One is you can either build an image or build a container locally on your laptop, and then you can move it to Polaris and then convert it into Singularity, or you can build it directly on Singularity. Also, I'm using the words image and container interchangeably. The word image would basically mean a static snapshot of the container, and container is the runtime instance of the image. So if I'm using interchangeably, I'm just trying to point to the same thing. Let's go to the GitHub where I'll walk through MPI code. Firstly, I'll just walk through how to build the MPitch image on Polaris. The thing to keep in mind is that when you qsub, you can only build the image on a compute node on Polaris. You'll need something, a flag called singularity fake root equals true, and that would help you build the image. Next thing is there's a definition file, which is nothing but a set of instructions on what are the libraries that you would need to actually run the container. And in this instance, I'm building an mpitch 4 image or container. And the one caveat over here again is that when you're building an mpitch image, you need to ensure that you pass this flag called disable wrapper path. This helps you, dynamically bind to the system mpitch when you're running it. And if you, oh wow, sorry, let's see. Doesn't show up yet.
Maybe a matter of stop share.
If I'm clicking on the link.
Yeah, it should, oh, yeah. There we go. Okay. Yeah, cool.
Yep, sorry about that. I was going through the GitHub example, so I think I spoke about this, that you need to have the singularity fake root equals true to actually build the image on the compute node. And the next thing I was speaking about was the definition file, where you give the set of instructions to actually build the image itself. And the one other thing which I also spoke about was the fact that you need to have a flag called disable wrapper path when you're building the mpitch, so that it dynamically binds to the system mpitch at runtime. If you don't do that, then you'd see a weird error where the way it scales is that it always runs on the rank 0 of every node, rather than it scaling on every rank. So that's how you would build this image, where you write this line where you say something like build fake root with the image name and the definition file, which you just provided. And once you have that ready, you can actually use it to run it. I'll just go through some of the important things that you would need to keep in mind when you're running it. There's a job submission script in this GitHub page, but if I'm breaking it down, you would see that you would need to load the module called Singularity, set the environment variables, which you usually set for internet access, have these couple of additional libraries or modules as well, and then ensure that the Singularity LD library path can see the system's library path. And then if you want to like run 16 MPI ranks on each node, you set that, and then when you're running the actual container itself, you need to bind some system modules so that the container can actually see those system modules while scaling up. So one would be the NVIDIA, there's PALSI, there's programming environment, there's libfabric. And once you run it, you would be able to see that it scales up. If you want to run on Polaris GPU, it's quite similar, just that when we're using a NVIDIA GPU image, which NVIDIA ships out. And again, we're also ensuring that the mpitch within that NVIDIA image has this flag set, the disable wrapper flag set, and that helps in scaling on the GPU as well. Couple of things to note is that you don't really need to have the application itself inside the build image, inside the image itself, or inside the container itself. You can afford to have it outside, and then you can point it while running. And Singularity has this feature where it will run it against its environment without having to copy the entire application itself. And we have a few containers pre-built, so which you can use readily out of the box. There's some databases. There's a TensorFlow on Polaris, and there's MPI, which is mpitch on all these machines. You can just pull them and run it against your application as needed. I think that's pretty much it about containers. So if you have any questions, yep.
Thanks. When you're talking about performance of containers, you're talking about comparing two applications running right on top of the kernel. But if you bypass the kernel, the block device, the file system, we've built and measured that as a user board driver. It's almost tripled the performance. So Sandia has a microkernel OS called Kitten, and then they have a way of interoperating with something like a container. Does Argonne have anything like that? No,
not that I'm aware of, at least. But that's an interesting thing. Well, something which we haven't looked at, as far as I know.
I mean, the way you built NVMe offload was with SPDK, which was user mode driver. Same thing for persistent memory when Intel had 3D crosspoint. But you could do that for many things. I mean, just the tasking model is so heavyweight, and then the context switch, so that's where you're losing a lot of performance, and all of the stack is built on top of this. So it's a catch-22 by the time you get down into it. So how do you, anything running on top of a container, you're probably losing.
Well, I would, from what we noticed, at least like when we ran a couple of applications, one is a Cosmic Tag application, which probably Corey could speak about. The initial build and the first run tends to be the slow one, and then as you keep scaling up, you wouldn't see much of a performance degradation. We did not see that much difference, at least with some of the applications that we run. But I hear what you're saying, and yeah, at least with the applications which we are running, we did not see that much of a degradation.
I think I saw another question, another hand. Any more? Okay.
Hi, good talk, by the way. So I have seen you showed a container for PyTorch, and then you have showed a container for MPI. So now if I want to use PyTorch and MPI together, do I have to load two containers?
No. So the PyTorch container has MPI within it, and so does the TensorFlow one. So no, you do not need to load two containers. And there's a method called bootstrapping, which I probably did not show, where you can use a pre-built image and then run your own, instructions on top of it. And that way you can just expand on existing images or existing containers. So an MPI image can then have TensorFlow, and MPI plus TensorFlow can have JAX. You can do whatever you want.
All right. So let's thank Archit and Aditya for the talk. They'll also be here this afternoon during the hands-on session if you have more questions. So thank you both.